Hi everyone, I am Romain Berendonner. I am in charge of AdaCore Cybersecurity offering, and together with Paul Butcher, the lead engineer on GNAT Fuzz, we are going to tell you all about AdaCore plans in the area of cybersecurity and all about our upcoming Ada fuzzing tool, GNAT Fuzz. As usual, this presentation will be followed by a Q&A session where you will be able to ask any questions regarding cybersecurity at AdaCore. As our long-term customers know, we were doing cybersecurity even before it was a thing. The features of the Ada language, high readability of the code, strong typing, boundary checks, reliable exception handling, all help make Ada programs more secure than programs written in C, for instance. These features did not come by chance. We do believe in correctness by construction, software engineering methodology which puts the emphasis on 1. Avoiding to introduce errors. This is where Ada features like boundary checks, exception handling kick in, or where formal methods leveraging pre-post conditions and invariant are paramount. 2. Remove any error as soon as possible. This is where static and dynamic analysis are used. And 3. Generate evidence that the software meets its requirements, which can be done by showing the element of proof or test suite results. Over the past 20 years, we have done a lot in these areas. To sample a few, back in 2008, we showcased correctness by construction in Spark with our partner Altron, demonstrating that the NSA Tokenier access control system was compliant to the common criteria EAL5 requirements. We also improved our CodePeer static analysis tool so that it could highlight a number of relevant CWEs, common weakness enumeration, in your code. And as of GNAT Pro 22, the Ada runtime will be compiled with runtime checks, improving the default security properties of your application. Next slide. This is no longer enough, though. If you look at the CVE database, you will see that the number of vulnerability published increases exponentially, just like the number of high-profile attacks increases. Of course, one could challenge that these metrics are relevant and discuss the extent of unknown vulnerabilities and unknown attacks, but the truth is, our world is becoming even more information and thus software intensive, and that the opportunities for cyber attacks increase. The legislators worldwide have identified the issue and acted on it. In the aerospace and defense industry, it is specifically worth mentioning how information systems handling CUI and CDI information will have to be CMMC compliant. Everywhere, the security of information systems and of the software supply chain are attracting lots of attention. Next slide. In front of these new challenges, AdaCore pledges to help you build secure software in 2 different ways. We are providing application security tools for Ada, such as our CodePeer static analyzer or the GNAT Check coding standard checker. We will continue to improve these tools and fill new application security tools as the needs of the industry evolve. More specifically, Paul will present our fuzzing technology in the second part of this presentation. We will also provide documentation about the security of our own product. This will include a program to manage the potential and actual vulnerabilities in our products and software bills of material. Next slide. Let's start with our product security commitments. Next slide. Starting at the beginning of next year, we will put in place a program for the coordinated disclosure of the vulnerabilities found in our products. Of course, as customers, you have always been welcome to submit support requests pertaining to potential security issues using either GNAT Tracker or our report@adacore.com email address. When the program starts, there will be a clear entry point for the community to report security issues as well. As they always were, all these incoming reports will be analyzed with security in mind. The main difference will be that actual security issues will be publicly released to the MITRE CVE database. Before this happens, however, we will leave a reasonable period of time to affected customers so that they can deploy the fixes we come up with. Those fixes will be made available to assurance users through web fronts, new releases, and, if they request so, on their sustained branches. Enterprise users will only have them through web fronts and new releases. Going one step further, starting with GNAT Pro 23 in 2023, we will make available ready-made software bills of material and vulnerability reports with GNAT, thus making the life of whoever needs to assess the security of our products easier. Next slide. This is a markup of the page that will be made available on our website to document our product security practices. You will find there our CVE disclosure policy, detailed advisories for any vulnerability, and links to the corresponding CVE entries in the MITRE database. Next slide. Looking more closely at our coordinated disclosure program, you will see that the submissions, no matter their origin, will be assessed against our security criteria and, if deemed appropriate, lead to the creation of a CVE. Our customers will have a 90 days period to deploy any fix before we publish the CVE on the MITRE database. This delay can be compared to the 45 days that the Carnegie Mellon CERT/CC Center gives and to the 90 days given by Google's Project Zero. Next slide. Switching to application security, there are a number of ongoing efforts that we wanted to make you aware of. Next slide. First, we are working at adding to GNAT Pro a number of compiler hardening features. These features will be useful to protect against glitching or memory attacks on systems that an attacker could physically access, such as a car or a phone. From a more technical standpoint, this will include things such as stack scrubbing to erase from memory sensitive data, conditional branches, control flow redundancy to avoid that, for instance, a single program counter glitch is sufficient to skip a critical decision branch, and Boolean hamming distance. Currently in development, these features will be made available soon in web fronts and will be of general availability with GNAT Pro 23. Next slide. A second effort we wanted to mention here is our work around record Flux and record Fuzz. These technologies were included in our portfolio thanks to the acquisition last year of Componolith GmbH, a software security company based in Dresden, Germany, and founded by Alexander Seignier. The jobs that these technologies intend to address is the implementation of secure binary communication protocols. Both use a formal description of these protocols that spells out the ambiguities that can be found in the natural language usually contained in the specifications. From this formal description, record Flux is able to automatically generate a Spark implementation of the protocol that can be proven to be free of runtime errors. Record Fuzz uses the same formal description to systematically test the conformance of an existing implementation to the description. Both technologies are in active development. If you are interested in experimenting with them, please reach out to us. Alexander will be available for the Q&A session should you have any question about record Flux or record Fuzz. Next slide. Finally, we wanted to let you know about our efforts in the area of dynamic application security testing. This effort is based on two ongoing R&D projects, HiClass in the UK with the support of the UK government, and Tageda in France with the support of the Ministry of Defense. Both aim at developing automated testing strategies, fuzzing for HiClass and property-based testing symbolic execution generated tests for tag Ada, along with consistent coverage and binary test formats for thoroughness and speed. The beta program will start in Q2 of next year, and these technologies will be of general availability with GNAT Pro 23. Now, enough with slideware, and over to you, Paul, for the GNAT Fuzz demo.
Thank you, Roman. So as Roman said, I'm going to go give you a bit more of a deeper dive into GNAT Fuzz, which is an automated testing tool that we've been working on within the high-class R&D program. So GNAT Fuzz has four main modes. Firstly, it can identify fuzzable closures. So these are subprograms within your Ada package specifications that we can automate the fuzz testing solution for. And at the moment we support basic scalar types, but as we progress with the technology, we will eventually support more and more complicated Ada types. Secondly, the tool can generate the fuzz test harness itself, and then it can produce the initial set of test cases, otherwise known as the starting corpus. And this is the set of test cases that is passed into the fuzzing mutation engine to then produce further test cases. And then finally, the tool builds and executes the fuzzing campaign. Behind the scenes, we're using an open source fuzzing technology called AFL++. And then if we open the hood of GNAT Fuzz, you'll see a number of modules, some of which we've developed through high class, others we already had in-house at AdaCore. libadalang is a tool that understands the semantics of the Ada programming language. And we use this technology extensively to analyze the software application under test and build up a fuzz test harness. And we also use this technology to produce the starting corpus, where we take values based on the types of the parameters of the subprogram that we've identified as our test injection point, and then we can stream those values into a binary test case file. And then we also use libadalang to produce all of the scripts that we need to build and execute the campaign. Quite early on, we produced a GCC compiler pass for AFL, and this instruments the code around the basic blocks, and it allows AFL to understand when it's found new paths through the control flow graph of the application under test. And we've since migrated that technology to AFL++, and we've upstreamed that into the public GitHub repository. We've also developed an AFL runtime library, and the purpose of this module is twofold. On one hand, we have an Ada binding to the C runtime library within AFL, and this allows us to switch between the different AFL operating modes. And then on the other hand, this library encapsulates the capability to encode and decode the binary test case files. And in here, we try and keep our test cases as tightly packed as possible in order that we don't waste mutation cycles with generating test cases that are invalid. And it's also within this library that we enforce what we call the stop criteria. And this is a set of user-defined rules that stipulate how long the fuzzing campaign will run for. GNAT coverage is AdaCore's coverage solution, and it supports statement decision or MCDC. We use this technology within GNAT Fuzz to produce a coverage build by instrumenting at the source code level. And then we execute the coverage build with each of the test cases that the fuzzer has found, and we can produce a dynamic statement coverage analysis that we can feed back to the user in near real time. We've also been experimenting with a symbolic execution add-on capability, and here we're using a tool called SymCC, which is an LLVM compiler pass that adds a symbolic execution runtime into the test harness. And we can use this capability with our GNAT LLVM front-end compiler such that we can concomitantly execute test cases, and then we can step back through the control flow and work out what the inputs would have needed to have been to take diverging paths within the control flow graph. And this allows us to feed more interesting test cases back into the fuzzer and ensure we explore more of the code base. And we've also looked at the AFL++ custom mutation API. And here we can intercept the test cases as they're being mutated, but prior to test injection. And we can either sanitize the data or we can mutate them ourselves with an understanding of the actual ADA types that the binary test case files represent. This capability is being integrated into our GNAT Studio IDE, so there'll be a menu option to analyze what we can fuzz test, then we can generate the test harness, generate the starting corpus, and we can execute the fuzzing session all through the IDE. But like the majority of tools within AdaCore, it's also fully invocable from the command line, and this allows you to tool chain it in whatever way you want to, and also include it into things like DevSecOps pipelines. Okay, so I'm just going to give you a quick demonstration of the tool. So if we launch GNAT Studio on an Ada project, then we can see that yes, this is indeed an Ada program. There's some package specifications and bodies. And what we now have is a new menu option at the top called GNAT Fuzz. And we can select GNAT Fuzz and choose to analyze projects. And this will identify all of the subprograms that we can fully automate a fuzzing session for. So all of those subprogram signatures that we can generate a harness for now gets this additional icon decorated on the source code. And it's also listed in this view at the bottom. So if we go ahead and select a subprogram and choose to generate the test harness, then we're immediately offered the option to switch to the harness project. And what we've now done is we've wrapped that user project with a fuzz test harness. So you can see that the user project is still there, but we can now fuzz test it. We've also got an example of the stop criteria. And this one is quite simplistic. It just says stop the campaign when the statement coverage reaches 100%. But we can make we give the option to the user to make this as complicated or as simplistic as they want. So now we've generated the harness, we can go ahead and start the fuzzing campaign. And the tool in the background is going to now produce all the various builds for AFL, for coverage, and it's also going to produce a build to create the starting corpus. And we can see here that it's already generated 729 test cases. And now it's going to minimize them down to the optimal size. And it's actually found that only 4 of them cover unique paths through the control flow. Now it's going to detect how many nodes are available, and it's going to run up an AFL fuzz process on each of the cores that it can utilize. And in this case, it's utilizing 4. The coverage is immediately coming back, and we can see it on screen. And we can also go and look at the source code itself, and the coverage will get decorated. So green means that the fuzzer has hit this line, red means that it hasn't hit it yet. And then in the dialog at the bottom of the screen, you can see all of the test cases that the Ada runtime constraint checking capability has found have crashed the program. And what we can do with those test cases is that we can expand them, and the tool will dynamically decode them. So these are binary test case files. The tool will decode them on the fly and give you a human readable visualization of the actual values that the test case represents. And then if we click on the test case, the tool will actually execute. It will rebuild the test harness in debug mode, and it will execute that test case. And it will take you to the point where the exception is raised. And here you can see the call stack. And we can use GDB, which is built into the IDE, to work out why the constraint error was raised. And in this case, it's because this calculation has resulted in an overflow. So at this point, we can correct the error, and we can very, very quickly rerun the fuzz test. And we quite like this approach. We feel that this is pushing the technology into the hands of the developer as part of our continuation of moving towards the shift left movement. But we thoroughly expect that for longer running fuzzing campaigns, we will also need to be able to support the technology on a client-server architecture. And that's also something we're actively working towards. Okay, so that was a very quick whistle-stop tour of GNAT Fuzz. And we're very open to Q&A. Thank you.